Okay, so imagine for a second that you're holding one of those standard plastic rulers.
The yellow one from school.
Yeah, exactly. And you look at the little tick marks, 1 inch, 2 inches.
Yeah.
You just know, like with total certainty, that the space between inch 1 and 2 is exactly the same as between 9 and 10.
It's a fixed truth. It's rigid.
Right. It's
Yeah.
the assumption we navigate our entire lives with. It's just intuitive.
And for everyday life, it works perfectly, no question.
But what if I told you that it wasn't actually true?
Yeah.
What if distance and angles and the very shape of the universe aren't fixed laws? What if they're just, I don't know, settings?
Like sliders in a video game menu.
Yes. You can just tweak them before you start the life.
You're not describing science fiction. You're actually describing one of the most profound shifts in mathematical history.
And that is exactly where we're going today. We are looking at a deep stack of research on something called Cayley-Klein geometry. And I have to admit, when I first saw that title, I thought, okay, 19th century projective geometry, this is going to be a little dry. But then I started reading, and wow, this is basically the source code for everything.
It really is. It's a connective tissue. It links things that seem to have absolutely nothing in common.
We're talking M.C. Escher's art,
Yeah.
Einstein's theory of relativity, and the cutting-edge AI that powers our social networks.
They are all running on the exact same underlying engine. And that engine is built on this really radical idea.
Which is?
That measurements, how far away something is, what an angle looks like, they aren't fundamental. They don't just exist. They emerge from a boundary, a choice we make called the absolute.
The absolute. It sounds like a superhero movie title.
We're Cologne, yeah.
So let's unpack that, because it feels like the key to this whole thing.
Yeah.
Normally, I'd grab a tape measure. That's the distance. You're saying that's wrong.
I'm saying that tape measure only works because of the geometry you happen to be standing in. Think of it like this. You're in a big empty room. The absolute is just the walls of that room.
Okay.
Where you decide to place those walls, well, that determines the rules for how you move inside.
So if I move the walls or change the shape of the room, I change the physics inside.
Precisely. In Cayley-Klein geometry, distance is calculated relative to that boundary. You change the absolute, you change the definition of a straight line, you change how angles work, how distance is measured.
Where you stand dictates the geometry you see.
That's the line.
Okay, that is a trippy concept.
Yeah.
So let's get into the specifics. The sources talk about this family of geometries as the three brothers.
Right. This is the classification Felix Klein came up with. He realized you could group all possible geometries based on just one thing, what kind of absolute they use.
So let's meet them. Brother number 1 is elliptic geometry.
This is the world of positive curvature. The easiest way to picture it is the surface of a sphere, like a globe.
Okay, navigating a globe, I can see that.
So in this world, the absolute is what mathematicians call imaginary. It's defined by an equation like x squared plus y squared plus 1 equals 0.
Right, and since no real number can square to a -1, there are no real points on that boundary.
Exactly. You can't see it, you can't touch it. It's an invisible constraint. And because of that positive curvature, the rules are totally different. Take parallel lines, for example.
Or the lack of them.
Right. There are no parallel lines. None.
At all.
Think about it. You and I start on the equator, walking parallel. You're in Africa, I'm in South America. We both head straight north.
We feel like we're moving in parallel lines.
But what happens?
We bump into each other at the North Pole.
Exactly. The universe curves in on itself. All lines meet. So that's brother 1.
Okay. Now for brother number 2, the boring one.
I wouldn't say boring.
The normal one, then.
Let's go with familiar. This is Euclidean geometry, the common sense world.
High school math, flat paper, triangles add up to 180 degrees.
Correct. Curvature is 0. But here's the thing. In this framework, it's actually a degenerate case.
Degenerate. That sounds a little harsh for the geometry we use to build bridges.
It just means it's a special limiting case. It's this tiny slice sandwiched right between the other two. The absolute here is in a sphere. It collapses into something called a line at infinity.
A line at infinity.
It's a mathematical construct. And that specific setup gives you the rule we all learned. For any line, there's exactly one parallel line that never, ever touches it.
The Goldilocks zone. Not curving in, not curving out.
Just flat.
So Euclidean is just this weird middle child. But now, brother number 3, the star of the show, hyperbolic geometry.
And this is where it gets really interesting. Hyperbolic geometry has negative curvature.
The sources mentioned a saddle shape or a Pringles chip.
A Pringles chip is a perfect analogy. It curves up one way, down the other. But here, the absolute is a real boundary, a circle or a sphere enclosing the universe.
So a wall you can actually see.
You can, and the key feature here, infinite parallel lines.
Wait, infinite? How does that even work?
Because space flares out, if you're on a line and there's a point next to you, there are infinitely many other lines you can draw through that point that will never intersect your line. They just peel away.
So space is expanding or getting more spacious the further you go.
In a way, yeah. There's simply more space out there.
And the notes say this is the geometry of relativity and AI. So this isn't just a math puzzle.
Not at all. This is how parts of the universe actually function. And to see why, we have to look at how distance is actually measured. This is the real aha moment.
Right, the formula. I have it here. Distance is calculated using the natural logarithm of the cross ratio.
Don't let the name scare you. It's just a relationship between 4 points. Imagine you're at point A and you want to walk to point B.
Okay, A to B.
The geometry looks at A, it looks at B, and then it looks at the 2 points where that line would hit the boundary wall. The absolute. It just compares the ratio of the gaps between all those points.
And the formula has a logarithm. Why is that important?
Because of what happens when you try to walk towards that wall. In the hyperbolic world, you can see the circle around you. So you start walking.
It's like it's 5 feet away. I take a step.
And as you take that step, you get closer in the drawing, sure. But the cross ratio in the formula starts to explode. And since the distance is the logarithm of that ratio.
Oh, the distance shoots to infinity.
Exactly. The ruler you're using stretches out the closer you get to the edge. You can take infinite steps, walk for 1 billion years, but you will only ever get asymptotically closer. You can never, ever reach the absolute.
That's the edge paradox. To someone outside, it looks like I'm just getting smaller and slower. But to me, inside, I'm just walking normally through a space that goes on forever.
Precisely. You're traversing infinite space that's been squeezed into a finite boundary.
And this is where we get to Albert Einstein.
No.
Because this sounds a lot like the cosmic speed limit.
It should. It turns out when Einstein was formulating special relativity, he was basically doing Cayley-Klein geometry. He just used different words.
So in Einstein's world, what is the absolute?
The speed of light, little c.
Whoa. Okay, so the speed of light isn't just a number on a cosmic speedometer, it's the geometric boundary of space-time.
That's it. The light cone, the path light acts exactly like the absolute in hyperbolic geometry.
And this explains why we can't go faster than light.
It's the same paradox. You can't walk off the edge of the disk because it's infinitely far away. You can't accelerate past the speed of light because as your velocity approaches c, the energy required, the distance in velocity space shoots to infinity.
So it's not that your engine isn't strong enough. It's that the finish line is infinitely far away.
You're chasing a horizon you can never catch.
That makes so much more sense. And the Lorentz transformation, the thing that says time slows down when you go fast.
In Cayley-Klein terms, the Lorentz transformation is just a rotation.
A rotation.
A simple geometric rotation in hyperbolic space. That's all it is. Einstein was just rotating the walls of the room to keep the speed of light constant for everyone.
That's wild. So the math was just sitting there waiting for physics to catch up.
And that's the beauty of it. The absolute is the invariant. It's the one thing that never changes, no matter how you're moving.
Okay, so we have this invisible infinite boundary in physics. But how do we actually visualize this? Because my brain hurts trying to picture infinite space inside a circle.
It's a challenge, and that's where we turn to art. Specifically, the Dutch artist M.C. Escher.
Oh, I love Escher. The staircases to nowhere.
Right, but the sources point to his circle limit woodcuts. The ones with the interlocking fish or the angels and devils?
Yes, I know them.
Escher was actually talking with mathematicians. He wanted to capture infinity on a finite piece of paper. And he used what's called the Poincaré disk model.
Which is a way of mapping this hyperbolic space onto a flat page.
Right. The sources mentioned 2 main models. There's the Klein model, where lines are straight. It's good for algebra, but it squashes the shapes. It distorts angles.
And Escher cared about the shapes.
He really cared about the shapes, so he used the Poincaré model. Here, lines look like curved arcs, but, and this is the key, it's conformal.
Meaning?
It preserves angles. If a fish's fin meets its body at a 45-degree angle in the center, it's still 45 degrees at the edge. The shape is perfect.
So in those prints, the fish in the middle are, normal sized. But as you look towards the edge,
they get smaller and smaller and smaller. They tessellate perfectly until they're just tiny specks at the rim.
Right, they look like they're being crushed.
To our Euclidean eyes, they're shrinking. But in the hyperbolic geometry of the painting, every single one of those fish is the exact same size.
Wait, really? They're all the same size?
Yes. If you were a fish in that painting swimming from the center out, you wouldn't feel like you were shrinking. You'd just feel like the journey was taking forever because the space is stretching.
Escher was painting infinity.
By warping the visual map to fit inside that circle, he understood the edge was an unreachable limit, just like the speed of light is for us.
Okay, physics, art. But now the outline takes a hard left turn into artificial intelligence. How does this connect to computers?
This is the modern frontier for this math. This is why major tech companies are hiring geometers.
The sources mentioned the Euclidean bottleneck. Sounds like a traffic jam.
It basically is. For a long time, most AI models were built using standard Euclidean space. Flat, simple geometry.
Makes sense. It's the math we know. X, Y, Z axes.
Right. But think about how space grows in that flat world. The area of a circle grows polynomially. It's tied to the square of the radius, r squared. Double the width, get 4 times the area.
Okay, seems fine.
It is, until you look at real-world data. Things like social networks or language structure or biological family trees. They're all hierarchical.
Like a family tree, yeah.
Exactly. You have 2 friends. They each have 2 friends who each have 2 friends. The number of people grows exponentially.
It's not r squared.
No.
It's 2 to the power of r. It explodes.
It explodes. And there's the bottleneck.
Mhm.
We're trying to cram an exponentially growing tree into a polynomially growing box.
So the data gets crushed.
Distorted. To fit that huge network onto a flat map, you have to put people who are really far apart right next to each other. You lose the structure. It's like trying to flatten an orange peel on a table. You have to tear it.
And this is where hyperbolic geometry saves the day.
Exactly. Remember the fish? How the space stretched at the edge?
Yeah.
In a hyperbolic disk, the available area grows exponentially like e to the r as you move out from the center.
Oh, because the ruler shrinks, you can fit way more stuff at the edges.
There is significantly more room at the edges. It makes hyperbolic geometry the natural home for these hierarchies. When tech companies use hyperbolic embeddings, they're basically mapping their data onto one of Escher's disks.
That's brilliant. The space
Yeah.
itself branches out just as fast as the data does.
You don't have to crush the data anymore. You just change the room to match the shape of the information. And the results are, well, they're stark. Better models, higher accuracy, all because you stopped fighting the geometry.
So we've gone from lines on a page to the speed of light, to fish woodcuts, to the algorithms that run our lives, and it's all the same math.
It's all Cayley-Klein. It's all about choosing your absolute.
It really makes you look at the world differently. I mean, we take flatness for granted. We just assume a straight line is the shortest path.
Yeah.
But that's just our local settings, isn't it?
That's the core philosophical insight, I think. Measurement is relative. Truth depends on your reference frame.
Truth depends on your reference frame. That's a bumper sticker for the universe.
It really is. When you change the absolute, whether it's the line at infinity or the speed of light, you change the laws of the universe you're in.
Which makes me wonder, are there other absolutes?
That is the big question, isn't it?
Like, we assume the speed of light is the ultimate boundary. But what if it's just a local setting? What if we're just living in one specific geometric choice and there are others out there?
If you could change the boundary, you'd change the physics. Gravity might work differently. Time might not flow the same way. The speed of light might not be a limit at all.
We might just be the fish in the center of the painting, with no idea what's really happening at the edge.
Or we could be at the edge, thinking we're the center.
That is something I'm going to be thinking about for a long, long time. So for everyone listening, next time you look at a map, a star chart, or even just your friend list, remember, the shape of that data depends entirely on where you decide to draw the line at the end of the world.
Check your edges.
Exactly. Look at the edges of your own maps. Thanks for diving deep with us today. This has been the Absolute Geometry. We'll see you in the next reference frame.